All right, guys. Good to see you here. We're going to take a look at section 8.3 notes. My intention was to be there today, but just wanting to be home with my daughter as far as, just her overall well-being and her health. Everything's all right, but just, with everything in the current climate, just wanting to be cautious and things like that. So, all right. We have this section 8.3 notes here. You can see it's part of the notes packet. This has one big idea, okay, and we're going to get to what that is here in a second. A lot of it plays into what we've seen before, right? We've seen things with the reciprocal functions and how to do that. We're going to talk about those today, plus a little more complex of a function, and then really just focus on their domain here, all right? So a rational function is a function that you can write in this form. F of x equals p of x over q of x, where p of x and q of x are just polynomials there. All right. So like I said, we're going to really focus on the domain. The domain of any rational function is all real numbers except for the x values that would make the denominator equal to 0. All right, here are some examples of those here. So you can see that. You can see that it looks like A and, well, let's just start with A. A is one that we kind of have seen in previous days, where it has a vertical asymptote there and it has a horizontal one. All right. B and F are kind of new in the fact that they actually have two vertical asymptotes here, right? So that's a big thing to go through. All right, so those two, B and F, they have two vertical asymptotes. All right. When we're taking a look at this next one here, C, C, notice it doesn't have any vertical asymptotes, right? So it doesn't look like X is being restricted at all. Okay, D and E here, just as a point of reference, we will not be talking about these kind of problems here. Notice they have like a diagonal asymptote there. Okay, we are not going to be talking about those, but you will just in future years. All right. If we take a look here at these last two, this last one, notice there's just a hole in the middle, right? So it's going, it's going, it's going, and there's a hole, then it jumps to the other side of it, and it keeps on going. Or that's this one where it has one vertical asymptote, one horizontal one, and we're good to go. All right. Okay. So something I really want to talk about here, this main idea, and is continuing this discussion about discontinuity. All right. So unlike polynomial functions, okay, what I mean by that is just like x squared. Okay, x squared, it kept going and going and going. You may have to pick up your pencil when we are graphing these rational functions, okay? All that means is that rational functions can be discontinuous. Okay, that's all it means. What that means is when I graph it, I might have to pick up my pencil. Now, I don't have to do that every single time, but it just could be something that I need to pay attention for. And again, the main idea today is how we're going to pay attention for that, all right, or what we're going to do to find that out. Okay, on the bottom one here, x squared plus 1. I know something's discontinuous if the bottom will ever equal 0, depending on what x is. So can I plug a number in for x, square it, and add 1, and get it equal to 0? I don't think I'm going to be able to do that. And you can see that right here. Notice I don't have to pick up my pencil to continue the graph here. This one right here, okay, when we're looking at this right here, notice I'm graphing it, and then there's a hole right there. It looks like the hole is when x is -2, and then I just keep on graphing it. Yeah, so there it's discontinuous. I'm graphing, I'm graphing, I'm graphing. I reach a spot where there's going to be a hole. We'll talk about why that's the case in a second, and then I have to keep graphing it. This one is more like what we've seen where I've been graphing, it starts to go way down here. When I pick up the graph, again, I need to start from the top and then follow it right there. All right. So when we look at these here, this is all about continuous or discontinuous graphs here, right? And this phrase right here, points of discontinuity, are a big idea. So here's what it is. Point of discontinuity is a value of x that, a value of x that makes 0 on the bottom. All right. Okay, so let's take a look here. That's why this is continuous here, right? So if I look at just this blue one right here, you can see that when I am looking at this, there is no value on the bottom that would make 0. So in this case, it would just be no discontinuity. All right. Let's take a look at another one here. It looks like here that this one has a discontinuity at -2, right? If I put a -2 in there for the bottom, then we're going to have some issues for that. And this last one here would just be +2. Okay. So we're going to take a look at special looksies here at the two main types of discontinuity. One is a hole and the other is an asymptote. Okay. Now these red and green functions that I've circled here, one's going to be a hole while the other is an asymptote, or what we call just a non-removable discontinuity, right? One that we are pretty familiar with just on previous days. All right, so we could look at a picture here, but this is what it has. What I really want to get to is what makes a hole. Okay, what makes a hole? And if I just write this problem I've circled in red down again. What makes the hole is this idea right here. When a factor cancels, I'm losing my pencil here. It makes a hole at that number. Okay. So when a factor cancels, it makes a hole at that number right there. So my hole is at -2. And again, if we wanted to look at a picture, there it is. It's at -2 there. All right. Asymptote. Again, what an asymptote is here. Let's just write it down. So the equation was x + 4 over x - 2. My question is that really the same as this one. Do I see an x - 2 on top and bottom? The answer is no. And so when the factor doesn't cancel, then we have a vertical asymptote right there. Okay, we have a vertical asymptote. All right, let's go ahead and see if we can practice some of these ideas. All right. Now, this first question here, where it says, how do I determine at y and an x-intercept? We'll come back to that. Okay. Okay, remember when it has a hole, okay, that's just when it cancels top and bottom. When will it have a vertical asymptote? When it doesn't cancel on top and bottom. And then when will it have no discontinuities? That's when you cannot have a number make 0 on the bottom. More than likely, it's just usually for us if we square it and then try to add a number, right? So if we square a number, it's always positive. And then if we add to it, there's no way it could be 0. All right, so here we go. What we would do first here is grab a different color pen since my pencil is running out. So what we're going to do here, and this is what I want you to do every time. The first thing I want you to do here is I want you to list the points of discontinuity. All right. So how we're going to do that is maybe we need to factor. Okay. That might be a good strategy here. Nothing to factor on the top, but it looks like this is how it factors on the bottom. Okay. Now, in order for me to look at points of discontinuity, I now know it's +3 and +1. When I do this, I need to analyze each of these numbers because 3 is either going to be a whole or a vertical asymptote. 1 is either going to be a whole or a vertical asymptote. I don't know which one, and it doesn't have to always be one of each. They could both be in one spot. They could both be in the other spot, but they do have to be classified as either a whole or a vertical asymptote. All right. So again, here's how we do that. The 3 came from the x minus 3. Do I see an x minus 3 on top and bottom? I don't. So it's a vertical asymptote. Same thing with the next number, +1. Again, I want to classify it as a whole or a vertical asymptote. Okay, what the previous answer is has no bearing on it. So does x minus 1 cancel top and bottom? It does not. So there it is. All right. Let's take a look here at this middle one. Again, we're just trying to classify what the points of discontinuity are. Notice when I have this here, there is no number that makes 0 on the bottom of that fraction. So there's no points of discontinuity, which means that if there's no numbers to classify here, then I'm going to have no wholes and no vertical asymptotes. All right. No wholes and no vertical asymptotes. All right. Let's keep going here. I want to do 2 more. All right, letter C is the next one I want to do. Again, we're just taking a look at this. It might be helpful, again, if I'm looking at factoring, just to factor the entire thing anyway. It looks like for my points of discontinuity here, looks like I just have a -4 because remember, it's only when the bottom equals 0. All right, it's only when the bottom equals 0. Now I need to decide, is this a whole or is it a vertical asymptote? Does x minus 4 cancel on the top and bottom? It does. So therefore, it just has to be a whole, right? So I've only classified the only number that's there. All right. Let's take a look at letter F. And this is going to be the last one of these 6 that we can do. All right. For this one right here, we have probably some factoring to do. This is how it would look to factor. Points of discontinuity. -2, -1. That means I need to classify them as a whole or a vertical asymptote. Let's just kind of take it one at a time there. -2 came from x plus 2. It does not cancel there. All right. So -2 would be my vertical asymptote. X plus 1 does cancel. So its factor or its 0 of -1 is a whole there. All right. Let's go back up here and let's just get a quick reminder of what to do here, especially with how to find y-intercept. How do you find the y-intercept of any function? You plug 0 in for x and you simplify. Now, this is going to be a lot easier than we think because look, if I put a 0 in, looking at the original problem here, if I put a 0 at the top, it's just going to be 3. If I put a 0 in at the bottom, again, looking at the original equation, x squared, x, yeah, all of those cancel out. I'm just left with a 3 there, right? So my y-intercept, again, I plugged a 0 in for x, and now I got a 3 as an answer. Okay. My x-intercept is a little bit different here. How do I determine the x-intercepts? Okay. After the fraction is simplified, so basically what that means is after we have crossed out all the holes, so think about this here, the x minus 4s wouldn't be there. After the fraction is simplified, it's where the top of the fraction is equal to 0. All right. So again, right here for my x-intercept, there's nothing. Okay, there's nothing right here that cancels out. So it's just wherever the bottom is equal, excuse me, the top is equal to 0. So -3, excuse me, what plus 3 equals 0? -3 plus 3 equals 0. And x-intercept here, again, nothing to reduce. So it's just going to be 5, 0. On the bottom, we could just plug 0 in. If I plugged a 0 into the top, it's -5. Plug it on bottom, it's just 1. So it's 0, -5 there. Let's take a look at these last two. We'll continue here just with the y-intercept. Okay. The x, if I said that wrong, the y-intercept is right here. We'll continue with the y-intercept right here. Again, just plug it into the original. So if I plug 0 in, I know it's always left just with the number without the x. So it's -4 over -4. So 0, 1. Zero, 1. The x-intercept, again, what we're looking for is after it's reduced. So these are no longer here, right here. And it's just the x plus 1. So the x-intercept would be -1, 0. -1, 0. All right, last one here. Okay. Plug a 0 in on the top, I get a 1. Plug a 0 on the bottom, I get a half. So it's 0, a half for that y-intercept. The only thing that cancels, or the only thing that's on top actually does cancel. So there's nothing left on top, or just a actual 1, not an x plus 1, but just an actual 1. So that means there's no x-intercepts here. All right. If you would like to, there's a video here posted on the screen record or the Canvas section. It says that there's no voice. It's basically the same thing, but it has a lot more of these problems worked out. So if you want to try some more of these, and including even some of these on the next page, feel free to look at that video just to see if you have it checked out. All right. Make sure you read the rest of the daily schedule, the daily agenda, submit the PowerPoint on OneNote in the correct spot. It's really just a drag and drop, really identifying some of these features right here. All right. Last thing, 5th period, students L through last name Z, part of the blue group. You need to make sure that you check Canvas. Juniors, you're just trying to get that browser installed on your computer for Friday's e-learning. Sophomores, I guess that would just be you, Ivy, and Sophie. Check again the bottom right-hand corner of my Canvas page for the 5th period SEL activity. And there is a slide deck for you guys to look through. Please, hope you guys are doing well. And let me know if there's any kind of questions or comments about what you saw today.